Hi folks, we're going to take a look at number 11D on page 479. So they're asking us to factor this quartic polynomial. So if we take a look at this here, first thing I see three terms with an x to the fourth term, an x squared term, and then a constant term. So I might think of factoring this as a trinomial, but there's no two numbers that multiply to 1 and add up to 1. Okay, so I could think about using the quadratic formula. But if I check my discriminant, so b squared minus 4ac, I've got b squared, which would be 1, minus 4ac, 1 minus 4, negative number. So that's not going to work. All right. So when you've exhausted your traditional factoring methods, this is when we would go to the factor theorem. But I see here there's only two factors of 1, 1 and negative 1. So let's test that out. 1 plus 1 is 2 plus 1 is 3, so that doesn't work. But if I stick in negative 1, I still end up with 1 plus 1 plus 1, 3, not equal to 0. Okay, so that means factor theorem doesn't work either. So this is where we've got a bit of an issue, because none of our methods is helping. Now, that doesn't necessarily mean that this is not factorable. Now, one thing I want you to notice here, x to the fourth is always positive or 0, and x squared is always positive or 0. So at the very most, these two things add up to 0, and then you're adding 1. What that tells you is that there can't be any x-intercepts for this function, okay, because it's always greater than 0. So question is, does that mean it can't be factored? Well, what if it can be factored as two quadratics, neither of which have x-intercepts? Okay, now this is the type of thing that, given that this is on the course review, I wouldn't say that you would expect something like this on your exam, because it requires a bit of a trick, okay? And this is how we're going to think about this. Can I change one of the expressions here? And in particular, I'm going to focus on this middle term so that I can do some factoring. So when I look at the x to the fourth and then the plus 1, okay, I realize that if I had a different middle term, I could factor this. Imagine if I had either a plus or minus 2x squared. Okay, you realize that I could factor this. Not only could I factor it, but it would be a perfect square, because x to the fourth plus 2x squared plus 1 factors to x squared plus 1, x squared plus 1. And if it was a subtraction, it'll factor to x squared minus 1, x squared minus 1. Okay, but of course, I still, I don't actually have plus or minus 2x squared. I have x squared here. So here, this is where I think, well, what would I have to have here to make up for the fact that the original term is x squared? Well, if it was minus 2x squared, I'd have to have a plus 3x squared. Okay, that's not too useful, and you'll see why in a second, because imagine I had plus 2x squared. In order to make this x squared, I'd have to subtract an x squared here. And let's check that these are indeed equal. X to the fourth, good. 1, good. 2x squared minus x squared is x squared. Now, why is this more useful? Because it's a subtracting of a squared term. And what did we say that x to the fourth plus 2x squared plus 1 factors to? It factors to x squared plus 1 squared. And then I've got my minus x squared. And lo and behold, we end up with a difference of squares, which I can now factor very easily. So it's the first term, okay, plus x times that first term, minus x. And there we go. There's our factorization, x squared plus x plus 1 times x squared minus x plus 1. And if you check both of these quadratics, you'll see that neither of them have any x-intercepts. So check the discriminant on the first, the discriminant on the second, you'll see neither of them have x-intercepts. So while this doesn't have any linear factors, it can't because there's no x-intercepts, we see that it can be factored into two quadratics. So again, like I said, this is not something I would expect to see on an exam, but it does give you sort of a window into the types of tricks that people use to factor more difficult polynomials. All right, that's it for this one.